ماذا لو أن الكفاءات الجزائرية من كافة أنحاء العالم تجتمع معاً؟ ماذا لو أن هذه الأدمغة بمختلف تخصصاتها تتكاثف لتطوير التعليم والبحث العلمي للنهوض بالجزائر في مختلف المجالات؟ هل تعتقد أن هذا مستحيل؟ أبداً، فالحلم يتحول إلى حقيقة من خلال الشبكة العالمية للعلماء الجزائريين إيناس. رغم أن إيناس هي مؤسسة غير ربحية وتعتمد فقط على تبرعات الأفراد، إلا أنها استطاعت أن تبني جسوراً من التعاون وتبادل الخبرات بين أبناء وطننا الحبيب من الداخل ومن مختلف بلدان العالم، ساعية لصقل المهارات واحتواء المواهب وتبادل الخبرات وإيصال التجارب النافعة لخدمة الوطن.
Assalamu alaikum wa rahmatullahi wa barakatuh. Thank you very much for joining us in another monthly webinar of the project Advances in Geoenergies and Renewable. My name is Mohammed. I'm the project leader and the initiator of this initiative. And in this month webinar, we are very pleased and honored to welcome Professor Mohammed Farfour. Assalamu alaikum, Ustad. Thank you very much for accepting our request. So today our keynote speaker is going to cover very interesting topics titled Seismic Attribute and AVO Analysis for DHI, Current State and Future Trends. So first of all, I would like to quickly introduce our guest speaker. Dr. Mohammed Farfour has received a master's degree in geophysics from Boumerdès University in Algeria and a PhD degree from Chonam National University from South Korea. He worked as a postdoc researcher in Chonam University and as a reservoir geophysicist at the National Oil Company of Geophysics in Algeria before joining Sultan Qaboos University in Oman. At Sultan Qaboos University's Earth Science Department, he teaches courses and conducts researches related to seismic interpretation and reservoir characterization. He has given a number of technical presentations in numerous SEG events and other international events, and published several papers in different scientific and professional journals. Dr. Mohammed also received the Schlumberger Award for Young Geoscientist in 2013 and the Best Teacher Award in 2020. And today he's going to share with us his expertise. Doctor, the floor is yours.
Thank you, Dr. Amrouche, for your introduction. Can you see my screen now?
Oh, please share your screen. I think it's not shared yet. Yeah. Yes, please go. I think it's cut.
Can you see it now?
No, I can't see it. It's disconnected. So maybe you can go on share the entire screen as we did before, and then you can share the entire screen.
And now?
Can you go on presenter mode? Yes, full screen mode. It seems that we cannot really see the full screen. So did you try to click on share entire screen in your presentation?
Okay.
Okay, try to go on share entire screen, and then we can see the full screen. Okay, just give me 1 minute. Yes, please. Yes, share entire and click on the hide button. Okay. And yes, here we go. Please, tfaddal, the floor is yours.
Okay, thank you very much, Dr. Amrouche. So first of all, I would like to thank Inas for this kind invitation. And also I would like to thank Dr. Amrouche and his team for their great effort for making this kind of webinars. So the topic of my presentation is seismic attributes and AVO analysis for direct hydrocarbon detection, current state and future trends. So in my presentation, I will start by a brief historical introduction about the detection of fluid with the help of the seismic, and then I go a little bit to some theory about elastic properties and seismic properties and their relationship with fluids. After that, I will go to the amplitude variation with offset. So it means I will focus mostly on the amplitude before I go later on or in some other slides to the frequency, because I'm trying to talk about all the attributes which can help us to find hydrocarbons. Then I go also to introduce maybe some information about the background trends and fluid trends and how we can maybe distinguish them in in seismic and also in rock physics and petrophysics, because all these kind of detection, they are based on certain trends and deviation from these trends. I will try also to list the different AVO fluid indicators which maybe they have been proposed over the last 4 decades, since the 1980s to present. Then I will try to highlight also some of the recent techniques for fluid detections which are used nowadays, like for example, the machine learning, the data science, and how we are using them and involving them in this maybe challenging issue, which is fluid detection. Lastly, I will go to some examples from real data set. And lastly, some conclusions and remarks. So the detection of hydrocarbon with the help of seismic actually dates back to the 1960s, where Mike Forrest from Shell, he has observed bright spot or large amplitude anomaly, which turned out to be hydrocarbon saturated sand. And since that time, they call it in Shell, they call it bright spot. So people, they start to do maybe some studies and try to understand what is causing this abnormal amplitude expression or bright spot. So, and indeed, it helped them to find many discoveries in the Gulf of Mexico and in Louisiana and in many areas. So now, what those studies have found, which have been carried out to understand the AVO or to understand the amplitude or the seismic and fluid. The studies found that geological formations, actually, they can be characterized by their elastic properties. So we have some elastic properties which can distinguish geological formations from one another, and can distinguish also fluids types. So every geological formation is characterized by its unique elastic properties, like for example, the P wave velocity, S wave velocity, density, Vp to Vs ratio, bulk modulus, and shear modulus, and Poisson ratio. So in the normal conditions, most of the time, the Vp or the P wave velocity and S wave velocity and the density, they often show very high correlation. Any presence of abnormal conditions, like for example, presence of fluid, because we suppose and we assume that the fluid is not normal thing. In the presence of, for example, hydrocarbons, we will observe some kind of deviation from this good correlation between the P wave and S wave and density. So this is the key point which we are using in detecting hydrocarbons. And this was demonstrated and published by Smith and Gidlow in the 1987, and by Castagna and his colleagues in the 1998, and also by Foster in 2010. So they have found also that the presence of hydrocarbon, it can cause a drop in P wave velocity and a drop in density and drop in Vp to Vs ratio and Poisson ratio and bulk modulus. And as you see here, this is the formula, or this is the expression of the P wave velocity, is a function of elastic properties like the bulk modulus and shear modulus and the density. The same thing for the S wave. The good thing is that the shear wave or the shear modulus will not be influenced by the presence of the fluid. This is what will make the fluid maybe, or will make the seismic sometimes is able to distinguish fluid from non-fluid, because the Vp and the Vs, they will not behave in the same way. So in the ideal conditions and in normal conditions, we do not have any hydrocarbons, so we will expect to have very normal trend, very normal correlation between the P wave velocity and S wave velocity and density even. And the presence of fluid will cause a deviation from that trend. And then we can detect hydrocarbons. So now, if we try to go deeply a little bit about the elastic properties and how they can behave in the presence of fluid. So for example, in the presence of gas, what we will have very large drop in most of the elastic properties, including the P wave velocity, the lambda, the bulk modulus, the Vp to Vs, and the Cairo or the bulk modulus, and the Poisson ratio as well. But the problem in the gas is that we will not be able to distinguish between different saturations. Why is that? Because this drop, it will occur at very weak saturation. So it means less than 10% water saturation or gas saturation. It will cause this large drop, and it will be the same at maybe even at 90% of gas saturation. So it means we can we can drill a dry well simply because of these maybe false anomalies which are caused by very low gas saturations. In the case of oil, things will change a little bit. So we will have a drop, but the drop will be gradual, and it will change actually with the saturation. So this is in the case of clastic reservoirs. In carbonate reservoirs, things will change a little bit. Of course, because the carbonate, they are much consolidated and much hard compared to clastic reservoirs, and they have very large bulk modulus compared to most of the clastics, maybe 3 times what we can have in clastic reservoirs. The reason why we have very maybe smaller expressions in the gas case and in the oil case compared to clastic reservoirs. And this is the key point actually in detecting fluids with the help of seismic properties. So now this is in terms of elastic properties. So now how can we find hydrocarbon with the help of seismic? As we have seen earlier, most of the seismic, or all the seismic properties, they are actually controlled by elastic properties. So changes because of fluid, or changes in elastic properties because of fluid in the elastic properties here, definitely and certainly will cause changes in the seismic properties. The reason why we will use the seismic as a tool, because this is actually what we will get from the field. When we acquire the seismic data in the field, we will not get elastic properties, but we will get actually seismic properties. We will get seismic section or seismic volume from which we can extract this kind of properties. What are these properties? Or sometimes we call them attributes. For example, I can extract the amplitude, the frequency, the phase, even the acoustic impedance with the help of inversion. So all these properties, I can extract them, and I can see which one will be maybe influenced more with the fluid presence. So as I have mentioned, different fluids and different attributes, they will have different behaviors. So and one of the key attributes and one of the best attributes which has demonstrated a very good capability of detecting fluids is the seismic amplitude. And by the way, the bright spots which we have seen in the Gulf of Mexico, which were observed by Mike Forrest, they were mainly amplitude behavior. So the reason why people started to know what is the link between amplitude and between the fluid presence. And the amplitude is actually very promising since that time. So people, what they have done, they have found that if we can, for example, collect amplitudes at different, or recorded or collected at different angles, so what we can have some quantities, and we can quantify these changes from one offset or one angle to another angle. That variation, it might help us to find hydrocarbons. So because the hydrocarbons, or the hydrocarbon presence, or the fluid presence, will show us certain maybe unique or special variation from offset to another offset, which will be different from the variation or the changes of the amplitude caused by lithologies or by any other factors different than fluids. So this is what they have done in the 1980s, and they call it the AVO, amplitude variation with offset. So we try to evaluate or to assess the amplitude at different angles, and we see how it behaves. Will it increase or will it decrease? And so this variation, it might help us, for example, to find hydrocarbons and distinguish them from their background or from their host rocks. And in the 1989, William and Rutherford, with the help of this variation, they have found that we can classify the gas saturated sands into 4 classes: class 1, class 2, class 3, and there was another class which was added by John Castagna in the 1994. And this is the old style of the AVO. Now the AVO is more than that. So in the AVO now, what we do, we try to quantify the variation of the amplitude with the help of what? With the help of 2 main properties, or 2 main attributes or quantities, which are intercept, which is nothing but the zero offset amplitude, and with the help of also gradient. And what is the gradient? Is just how much my amplitude is changing from one offset to another. So the AVO practitioners or AVO interpreters, they have found that different fluids, they have different AVO quantities, intercept and gradient, and different lithologies, they have also different variation, intercept and gradient. Some other AVO workers or interpreters, they use P impedance, not the P impedance, but the P reflectivity and S reflectivity instead of the intercept and the gradient. But both of them, they will lead to the same point, that with the help of the variation of the amplitude, I can distinguish between lithologies and between fluids. So in most of the interpretation they were done based on AVO in the 1980s, what people they used to do, they used to combine the intercept and the gradient, cook them in certain way, or combine them in certain way, or merge them, or combine them, multiply them, or maybe adding them in a way that we will try to find a good quantity which can lead us, for example, or to guide us to find hydrocarbons. And seismically, those attributes, for example, the intercept and gradient, in the absence of hydrocarbon, they will show certain trends. But in the presence of hydrocarbon, they will show a different trend. So what we do usually in the AVO, we try to use the intercept and gradient in the background, or where there is no fluids, and we see the normal background. And in that case, where there is no fluid, we should have well-defined background trend. This is according to Castagna and Smith in the 1994. Any presence of any fluid will try to deviate us, and will try to cause a deviation from that trend of the background. So the reason why different peoples came up with different backgrounds. So we try to find different background in which we can find maybe much better deviations. So some people came with, for example, the P wave velocity and S wave velocity as plane or as a domain. And this is the domain of Castagna in the 1985. So he found that if I would cross plot the P wave velocity and against the S wave velocity, I will have good correlation between them. And in the presence of fluid, I will have a deviation from a line which I will call Madrock line. In the 1987, Smith and Gidlow, they come up with another domain which will define another background line, and that domain is in the P wave reflectivity and in the S wave reflectivity. Then in the 1993, Foster and his colleagues, they come up with another domain where we can find a better maybe separation or a better deviation which can lead us to find fluids. And they have defined that background as the fluid line. So they have used the intercept against the gradient, and any deviation in that domain, we will try to attribute it, or we try to relate it to fluid presence. So in the 1994, it means 1 year after, the Fretty and his colleagues, they have found, and they came with another domain, and they said, no, we will try to use the RP for the reflectivity of the P wave and the reflectivity of the S wave, and we might have a better result than the intercept and the gradient. Then in 2017, Leo and Ghosh, they have found that if we can plot, for example, our data in another domain, which will be the P wave, and it will be also the JP and JS. So these are the two attributes they have defined. So we can observe deviations between the fluid trends, and we can separate between, for example, the brine, between the oil, between the gas. Then in 2020, myself and Douglas Foster from the University of Texas at Austin, we came up with another domain. So what we have tried to do, we have tried to plot or cross-plot the gradient against the scale Poisson ratio, which was defined by Castagna in the 1994. And we have found that if we do that, we do this kind of projection or this kind of plot of the data in that domain, we will have most of the hydrocarbon in that quadrant, in the third quadrant, and the deviation from that normal trend, it will be controlled by the compressibility of the fluid. So the more we have compressible fluid, the more we will have deviation from this normal trend or background trend. So I can now summarize, for example, just a list of fluid indicators which were proposed since the 1980s until now. And of course, if you go to the literature, you may find maybe more than that. But here I just try to come up or to collect this list of published fluid indicators. In the 1980s, we used to use, for example, the intercept times gradient, and it was working especially for class 3 reservoirs or for young reservoirs, and especially gas. And then in the 1987, Smith and Gidlow, they have the open fluid factor, which is a function of the change in the P wave and the change in the S wave, plus calibration factor, which is G factor here. This G factor is a function of the P wave and S wave velocity ratio of the background. So all fluid factors, actually, they are working and they are trying to find a deviation from the background. So then they proposed also what they called pseudo-Poisson ratio or reflectivity, which is also the direct difference between the two reflectivities, or the P wave and S wave reflectivity. Then in the 1994, Fatty and his colleagues, they proposed another version or another form of the fluid factor, which was proposed by Smith and Gidlow, and they found we will not use the ratio of the P wave and the ratio of the S wave, but we will use the reflectivity of the P wave and the reflectivity of the S wave. So here the density term is included and is involved. And then Castagna and Smith in the 1994, they found that we will not use the RP and the RS as the Smith and Gidlow they have used. So, but we will try to use the intercept plus the gradient. So that if we sum the intercept plus the gradient, that might lead us to the same result as Smith and Gidlow. In the 1999, Gray and his colleagues, they have found that we can extract, for example, the lambda rho, or the first Lamé parameter, reflectivity from the gutters, and we can also extract the bulk modulus reflectivity from the gutters, and both of them, they are very sensitive to fluid because they are indicating the incompressibility. So we will expect drop in the incompressibility or change in the incompressibility from the gutters. And then what we can do, we can just invert these reflectivities in order to get the impedance, or we can get the direct lambda and the direct K, or the bulk modulus. In 2011, Brian Russell, in his paper, came up with another type of fluid indicator, and he called it the F, or the delta F. So the delta F is also, it can be extracted directly from the gutters, and he has demonstrated that it measures a very good deviation from a very clear trend. And also in the 2002, Ross, in his paper in geophysics, he found that if I just subtract the near stacks from the far stacks, I might come up with maybe some fluid expressions. Then this is the fluid factor which was proposed by Leo and Gosh, and these are the J parameter, JP and JS. And in 2020, myself, I have proposed another way to find hydrocarbon expressions by trying to limit the seismic data to certain angles. So what we can do, for example, we can go from very near gutters, from very near offsets or angles to very far gutters, and we will see where we can find the best angles which can show us the best expression of fluids, and we can call these angles as fluid angles. Then in the 2020, myself and Douglas Foster, this is the attribute which we have proposed. We have proposed that if we use the intercept plus gradient, which was proposed by Castagna and Smith, and we multiply it by the gradient, we might have maybe a better delineation and a better deviation from the background trend. And then we proposed another fluid factor, which is a function of gradient and intercept. And I will show you in the examples how it will look like if we apply it on real seismic. So now I was talking mostly about seismic properties and reflectivity-based fluid indicators. In the 2014, Brian Russell, in his paper in the interpretation, he tried to extend the AVO from reflectivity-based attributes to impedance-based attributes. So it means we will not limit ourselves on the reflectivity-based attributes like what we have seen earlier, but we will also include any impedance product which can be extracted with the help of AVO inversion. But if we go in the literature, we will find that Fatty and his colleagues, they were the first to observe that we can use impedances, but not reflectivities and not seismic properties in order to observe this kind of deviations. And at that time, they have proposed the fluid factor, which was in the impedance domain, but not the reflectivity domain. So they were the first, and they have done this in the 1994. Then in the 1995, Bry from Schlumberger, he has found that if I will cross-plot the VPVS ratio against the sonic log, so what I can have very clear distribution of different lithologies and different fluids types. So that time it was just VPVS and sonic. After 20 years, Abseth and his colleagues, they have published their paper and their book in quantitative seismic interpretation, and they come up with the rock physics templates. So what are the rock physics templates? They are just an improvement of what was published by Bright in the 1995. So what they have done, just instead of using the sonic, they have used the impedance. So we have in the rock physics template, what do we plot, or what do we cross-plot? We cross-plot actually the P wave to the S wave velocity against the impedance, and with the help of this cross-plot, we can have a very clear deviation which can be caused by the fluid. So we have seen now the different types of fluid detections, and here I can list a number of fluid factors which are used especially in impedance, not in seismic properties. So here I will start by the Fatty and his colleagues. So this is the parameter, or this is the fluid indicator which they have proposed. And then in 1997, Goodway and his colleagues, they have proposed another form which can help us to detect the hydrocarbon, and they call it the lambda rho, which is nothing but the impedance square of the P wave minus the double of the shear impedance square. And they have, so here, if we use the lambda rho has shown very good capability of detecting fluids. And also they have proposed the lambda over mu, which is also a very good indicator of fluid in the impedance. Then in 1999, Connolly, he has proposed what we call now the elastic impedance. And Whitcomb in 2002, he proposed the extended elastic impedance, or the EEI. So what we can do here, we will just try to correlate, or we'll try to rotate the P wave and the S wave and the density which are extracted from the impedance or maybe from the logs. We try to rotate them at different angles. And by this kind of rotation, we can find some modifications of these logs which will coincide and which will show very good consistency with the fluid logs. Then in the 1999, Gray and his colleagues, they have found that if we subtract the bulk modulus times the density minus the bulk modulus minus the density and the mu, we can have maybe a better fluid expressions. And then in 2003, Brian Russell, he came up with another fluid, and he called it the rho F. And he said, I will just generalize what Gray and others they have found, and I will use a constant which will be C. And this general constant is a function of the VPVS ratio for the dry rock. And in 2006, Quackenbush has proposed the Poisson impedance. Poisson impedance is some kind of impedance which is more related to Poisson ratio. That's why he called it the Poisson impedance. And then another fluid factors came up, were proposed by Abseth in his paper in 2015, which is data-based or data-driven method, which will measure the deviation from a cross-plot in the rock physics template, and it will try to create a fluid indicator from the impedances, from the acoustic impedance or from the P impedance and from the VPVS. And then Castagna and Jiang in the 2019, they just came up with a more generalization form or generalized form of the attribute which was proposed by Brian Russell. And they said, instead of using this C constant, we'll try to use the impedance calculated only for the frame rock. And we will subtract it from the impedance of the saturated rock, and this will help us to express and to highlight the fluid behavior. So this is about the amplitude. Now, frequency. So the frequency also, sometimes they have shown a very good indication of fluid presence. And in the 1990s, another technique which is related to amplitude, to frequency, but not amplitude, and we call it spectral decomposition. What do we do in spectral decomposition? We try to extract different bands or individual frequencies and use them and try to interpret them instead of interpreting the broadband. So what they have found that if we use these individual bands and we try to show them all together, so we might see some behavior which can be associated or can be attributed to fluids. And the example which they have shown and demonstrated in their paper in the Geophysics, Journal of Geophysics, they have found that the presence of the oil here, it's not the gas, is causing a drop in the frequencies and is moving the data to lower frequencies. So it means as they are changing the frequency, they are finding that they can have different fluids and different saturations. And they have tested this also on well logs, and they have done the fluid replacement modeling, and they have found that the presence of the fluid will actually cause the data to move towards low frequencies. So it means high frequencies, after introducing the oil in the area or in the parameters, we will have lower frequencies, which can be a very good indication of presence of hydrocarbons. So they have used the spectral decomposition, which was initially proposed in the 1990s, especially for thicknesses and for mapping channels. They have used it for fluid detection. Now, if I will talk about recent techniques, and I will talk about what we are doing in today's oil industry. Now, with the revolution of the data science and the machine learning, which are very trending nowadays. So people, what they are doing, they are using data science and they are using machine learning in order to extract more features and more maybe properties from the data as we have never been able to do. So now, for example, with a simple command in Python, you can cross-plot all the fluid which I have listed earlier. So for example, and you can see the correlation and the similarity between all the attributes or all the fluid factors, and you can choose which one is the best. And you can also control, and you can see the performance or QC the performance of all the attributes, and then you can decide which one will be the best for you, because for sure you don't need to use all the fluid factors which I have listed. So you can test them all, and with the help of the data science and with the help of Python and with the help of open source programs, you can cross-plot them and you see which one will be the best and which one will not work in your cases, because as we will see later on, there is no fluid indicator which can work for all conditions. There is no magic. There is no tool which can be standard for all geology. And now machine learning. Machine learning is a kind of branch of science which involves computer science and statistics and probability in order to let the machine train in order to do the job for us. So we have now very long list of machine techniques which can do the job for us. And by the way, the machine learning is not a new branch. It is just the trending branch of science, because we are using machine learning maybe since the 1990s or the 2000s. We are using the neural network, and you can find them in most of the software in oil industry. But now, because of the advances in computations and in computer power, so there is a tendency to go to automatic tasking and automatic work and detection with the help of the machine in order to benefit from the computation power which we have today. So, for example, the machine can help us in the, for example, in the regression or in the prediction. It can help us also in the classification. It can be maybe supervised classification or unsupervised classification. So we can do it for many things. We can also to do, for example, reduce the dimensionality or to reduce dimensions. So here I can list some of the main applications which we are using or in which we are using the machine. For example, many interpreters that are using the machine in order to maybe find a relationship between seismic expressions and seismic attribute or seismic data and direct measurement or log measurement or direct logs which are directly linked to fluids, like for example the water saturation log, like the resistivity, like the CMR free fluid. So what I can do, I can train my machine in order to find a link or relationship between any of these properties. And then once I find that there is a relationship, I can apply it on the whole cube. We're using also the machine to predict sometimes some logs or some information or some features which are missing for us in order to do or to complete the work, especially in rock physics. In rock physics, as we have seen, we're cross-plotting or plotting or analyzing different elastic properties. So in many cases, we might have an S-wave velocity which is missing. So we can use here the machine learning in order to predict or to create some maybe S-wave logs which are created by the machine by some certain type of training and validation and QCing it, and then we can use it as any original logs. And some interpreters, they are using the machine in order to combine different fluid factors. For example, I have shown now around maybe 10 fluid factors. You can combine them all after, of course, after filtering them and finding the best of them. You can then combine them all in one attribute, and you can call it, for example, fluid probability cube, and that will be, of course, more reliable than using single attribute. Some interpreters, they are using the machine in order to carry out supervised classification. So I can classify maybe my data, or I can generate a cube which will show me where do I have maybe fluid expressions and where I do not have, yes and no. So this is a supervised classification. And sometimes unsupervised classification, it means I will just try to train the machine in order to come up with classifications, and then it's me as interpreter to find what are these classes, with the help, of course, with the geology and with the help of well logs and maybe previous wells which are drilled in the area. Some interpreters, they use the machines in deep learning. For example, they are using some pre-trained neural networks or networks which can help them to implement or to do or to apply the training which was done on maybe previous experience or previous data set, and to bring it to a new data set. And this is what we call the pre-trained networks. And most of the software now, they include all these kind of machine learning tools. And also you can find also, if you go to the literature and you can go to some maybe packages which are open and they are free, so you can use all these applications of the machine learning without any maybe charge. Now, if I will come to the limitations and uncertainty, of course, there is no science, there is no technique, there is no approach which does not have limitations. And I have to say here that, of course, the fluid factors, as any other approaches, they will have uncertainty and they will have limitations. Why is that? Because extracting the fluid indicators from the seismic is actually an ill-posed problem, which means that we will have a non-unique solution. There is no unique solution. So it means for sure we will have some false anomalies which are indicated and which are identified as a fluid, but they are not fluid. So how can I eliminate these kind of cases? Of course, by experience, and of course by testing, and by doing it again and again, and by calibration. And also I had to know that all the fluid factors which we have seen and which are existing now in oil industry, most of them, they are based on trends in cross plots. So it means that I have a normal trend of the background, and I will try to see the deviation from that normal trend, and I will interpret it to be a fluid. So the problem is that many cases, the deviation, it may be caused by some abnormal lithologies or maybe some abnormal pressure, which will cause a deviation from the normal trend. So sometimes also the noise can cause some problems and some troubles for us in the interpretation of this kind of deviations. So, and also most of the reflectivity-based fluid indicators, they assume that we have a very good correlation between elastic properties and the trends are distinguishable. But in some cases where we have very compacted rocks, sometimes we cannot distinguish the trends of the different lithologies and the different fluids. Sometimes it's because compaction, and sometimes because of geology, sometimes because of maybe noise. Also, I have to mention that there are some attributes which are difficult to model, honestly. For example, like the spectral decomposition. Spectral decomposition is not easy to model it. But amplitude-based attributes, they are very easy to model. So we can model them and we can see how the data will look like in theoretical way using the available data set. But interpretation of spectral decomposition sometimes is ambiguous because of what? Because we cannot model the answer, and we cannot have a prior knowledge about the response and about the expression in the frequency domain or in the frequency, so that we can justify it once we find it. Because we believe that in seismic interpretation and in general in geophysical interpretation, we believe that if we can model, then we can interpret. And good interpretation comes from or start by good modeling. Another thing I have to mention about the machines and how they are implementing them. The trained machines, sometimes they will succeed, and in many cases they may fail. And for example, myself, I have tested the machine and many different tasks. In many cases, the machine will fail. And I have to do it again and again and again, and you have to validate it, you have to QC it, you have to. So in many cases, actually, we are forcing the machine to do the job for us. That's why, as an interpreter, I will use the machine. I will benefit from the machine learning advances and from the new findings and the new results, but I have to QC my results and I have to validate my results, and I have to do the training once and twice and 3 times and again and again. Lastly, I will go to examples. Some examples, they are from real data set and some from theoretical data set. So the first example is is using data samples which are collected by Castagna and Smith. They have collected 24 samples of data sets from different fields. The data set includes P wave velocity, S wave velocity, and density, and they have used this data set in order to test different fluid factors, and especially the fluid factors which they were proposing in that time. So here, what I'm doing here, I'm trying to use different fluid factors, and I'm trying to see which one will provide us best distinction and best discrimination between the fluid and the non-fluid anomalies or amplitudes. So I have found that different fluids, different fluid factors, they have different performance, and also they have different quantities and they have different calibration factors. So it means some factors will work in certain geology and will not work in other maybe geology conditions. And here, all the fluid factors which are extracted from the Castagna dataset, they are cross-plotted here using Python. So, and here we see that some of the attributes, they are almost showing very high correlation, like for example, the fatty attribute and Smith. They are showing very high correlation. Some they are showing less correlation. So it means I can benefit from them, and I can integrate them, and I can use them as maybe independent or additional information. And also we can use the machine, not the machine, but the Python, for example, to plot the different attributes and to see which one will perform the best. And here we are using, for example, the definition of fluid factors of Castagna. Castagna is saying that the best fluid factor is the best attribute which can show us different responses between the top and the bottom. So here this is the top of the reservoir and this is the bottom of the reservoir, and we see that all or almost all the attributes are showing different responses at the top and the bottom of the reservoir, which will make them very distinguishable and very clear that they are not the same. So it means here we can discriminate between different types of fluid, because at the top, of course, we have hydrocarbons, and at the bottom we have water. And the other example is from Smith and Gidlow. So here I'm using the data set of Smith and Gidlow in their paper in the 1987. And here from this data set which they are using, so they have tested their fluid factor and their Poisson or scale Poisson ratio. And here we see that the top and the bottom, they are appearing among all the rest. And I cannot see the rest. Why is that? Because this response or this expression is due to fluid. So nowadays, because we can use open source programs and we can program and we can do modeling by ourselves, we can test different fluids using our own programs, because maybe or unfortunately you cannot find a program which will bring you all the fluid factors at once. So, but now with the evolution and with the advances in computer programming, we can do it by ourselves. So here I'm comparing between the intercept, the gradient, and the scale Poisson, and the fatty, and the Smith and Gidlow, and the fatty fluid factor also, and another new fluid factor. And I see that I can distinguish between the fluid and the non-fluid at certain type and at certain degrees with the help of computer programs. The last program or the last example is from Northwestern Australia, and here we have a field which is called Poseidon Field. It's from Browse Basin. So here we have a petroleum system which is working here in this area, and all the reservoirs are gas producing, and these reservoirs they belong to the Plover Formation, which is deposited in fluvial deltaic environment during the early to middle Jurassic. So here we have shale and we have sand, and we do have some complexity because of the geology and because of tectonic and because of also of sequence stratigraphy. So we have a good number of wells. So for example, we have 3 wells which we will be using for the calibration and for testing the different fluid factors. We have, for example, Poseidon 1 and Poseidon 2. So we'll use Poseidon 1 and Poseidon 2 and Kronos. In the Poseidon 1 and Poseidon 2, we have quite thick reservoirs, and in the Kronos, we have quite thin reservoirs. So we have reservoirs, but with different thicknesses. Why? Because the positional environment is forcing and is creating this kind of reservoirs which are changing laterally from one point to another. So this is Poseidon 1, this is Poseidon 2, and this is Kronos 1. So here we see the reservoir at Kronos 1, and here we see the reservoir at Poseidon 2, and the reservoir at Poseidon 1. So we will try to see them in the seismic, and we will try to use different fluid factors and to see if they are able to do the job of detecting the fluid. So firstly, we have to start by maybe doing some kind of structural or classical interpretation of the seismic by identifying the different key horizons. For example, here this is our regional seal, which is Jameson Shale. It's a very large shale which is dropping and which is covering most of the reservoirs which are in green color here, the peaked horizon, which is the Plover Formation. And we see here many different types of faults, and all these faults, they are created in an extensional regime during maybe the Cretaceous. So this kind of faults, they are creating many structural traps in the area, which might be not easy to detect with the help of classical seismic interpretation. So the first thing we have to do, we have to start by the modeling. So here we have, for example, the different types of elastic properties or different logs. We have impedance, and we have the VP, and we have the VS. So what we can do, we can try to model the seismic response and the AVO response, how it will look like at the well location. And we see that different reservoirs with different thicknesses, they have different responses. So this is the thick, we have a thin reservoir, and we have another reservoir, and we have a third reservoir, which is quite thick. We see that the amplitude responses are different. And we believe as interpreters that good interpretation all the time starts from good modeling. So we can use now the different elastic properties and to see where we can find the fluid, and we can benefit also from the rock physics, and we can cross plot, for example, the VPVS against the impedance, and we see if we can see any kind of deviation which can be associated or it can be attributed to fluid, for example. And this is exactly what we have done. So now we will start, of course, the work or the interpretation work of the AVO analysis by extracting the intercept and the gradient, because they are the principal attributes which can be extracted from the gathers or from the seismic. So here we have the intercept, and here we have the gradient. The intercept is showing that most of the reservoirs in the area, they are showing very weak reflectivity or weak amplitude. Why is that? Because we have low contrast in impedance between the reservoir and non-reservoir areas. But the gradient is showing us that we might expect some good variation compared to the background. But also, unfortunately, we will have some non-reservoir zones which will show also large variation. So it means the intercept and the gradient will not be sufficient in order to come up to a very good conclusion or interpretation. So here, what we can use, for example, we can use the intercept times gradient, and we can use the intercept plus the gradient, which is Castagna fluid or scale Poisson ratio. And we see here that we started seeing some fluid expressions, but still the other non-reservoir formation are showing very strong reflections. But in the intercept and gradient, we see here that we have very weak expression or magnitude or amplitude. Why is that? Because the intercept is already weak. When we multiply it by the gradient, it will reduce the gradient effect. And then we see that the shale, they have larger intercept times gradient compared to our reservoirs, which means that we have hidden our reservoir. So we have masked our reservoir because we have used this intercept times gradient. So now what we can do, for example, we can test the fluid factors, which I have mentioned in the list earlier. So for example, because I have the P wave velocity and S wave velocity and the density, so what I can do, I can test the different fluid factors and see which one will show me best performance, and then I will try to use it. So here, this is the best performance. I see that, for example, one of the fluid factors is showing me the best performance when the calibration factor is around 0.45, but the rest of the fluid factors, they are not showing me good maybe results. Why is that? Because the problem is here is that the velocity and the P wave velocity and S wave velocity and the ratio of the two velocities is changing actually laterally, and this will be against the assumptions which we have in most of the fluid factors. So now when we use these fluid factors which we have calibrated to the geology, for example, if I use the intercept or the scale Poisson ratio times the gradient, I see that now I could distinguish between the reservoir, which is in the blue or the light blue, and between all what is not reservoirs. By using what? By using the scaled Poisson ratio times gradient instead of intercept times gradient. And also I can use the attribute which I have shown earlier, but at this value of the calibration factor at 0.45. And I see that I could see and I could observe the fluid expressions from my seismic by combining the intercept and the gradient. And here, this is another well where which was not used. This is another seismic section at one of the wells which was not used in the calibration. And we see that we have very good expressions of fluids, which is making the fluid very distinguishable compared to the background. And here, this is a random line which is collecting or connecting between all the wells and crossing along all the wells, Poseidon 1, Poseidon 2, and Kronos 1. And I see that here I have the fluid expressions, and I have them also in my Poseidon 2, where I have one shallow and one deeper reservoir. And in the Kronos, because it's a very thin reservoir, so I see that I have very weak expressions, which is coinciding and which is consistent with the geology and with the logs which I have. Because if I have found an anomaly here, large or as large as I have found in Poseidon 1 and Poseidon 2, I have to question myself. And I have to ask myself, why do I have the same anomaly while the reservoir here is very thin and it might be easily masked by other beds or other geological formations. So this is another fluid factor at the same calculated over the same random line, and is showing also similar results, and also is showing the fluid expressions at Poseidon 1 and Poseidon 2, but is showing very weak expression at the Kronos 1. For spectral decomposition also, it was tested here, and it's not showing very good maybe discrimination between fluid and non-fluid. And I told you that, for example, spectral decomposition, one of the challenges in the interpretation of spectral decomposition is that we cannot model it. We have just accept the result which we will get from the spectral decomposition. Lastly, we go to the seismic inversion. So in the seismic inversion, we try to remove the effect of the webblet, and we try to convert the seismic traces or the gathers to impedance products. So for example, I will extract, for example, the ZP or the P impedance and the S impedance and the density, from which maybe I can calculate other attributes as I have seen earlier. So for example, here, this is the same line or random line which will connect or will come across or will go across the three wells, and I see the impedance that it is changing and is weaker or is lower at the two wells, while at the Kronos well here, I don't see, I see very high impedance, but at the Poseidon 1 and Poseidon 2, I see that I have lower impedance, which might be caused by the fluid and by the fluid presence. So here I have also the VPVS, and I have the other impedance. So I see that I have a better P wave to S wave ratio. It is showing me that at the reservoir level, I have a drop in the P wave to S wave ratio, which is consistent with my theory. And from the impedances which I have extracted, or we can extract, we can also calculate, for example, and we can have the lambda over mu, and we can have the Russell fluid attribute. And we see, for example, here that the reservoir is showing very low Russell attribute magnitude, which is caused by the fluid present in the reservoir. Lastly, once I extract all my fluid expressions and fluid attributes, and so now I can use the machine learning to do the rest of the job, which is the characterization, for example. So what I can do, I can combine all the fluid indicators or fluid attributes. Then I can train the machine to find the fluid for me, or maybe fluid probability cube. I will produce it from all these attributes which I have generated. And sometimes I can go even beyond that. I will, for example, create gamma ray cube with the help of the neural network. So with the help of the neural network, I can combine different attributes, which will help me to create maybe a gamma ray cube from these seismic attributes. And also, for example, I can use some pre-trained networks in order to find, for example, some faults, and to give me, for example, some gas chimneys, which will indicate for me the presence of maybe traces of gas which are caused by the migration of the fluid from the source rock to the reservoir rock. And this can help me also to QC or to validate, or maybe to see the seal efficiency. Because if I see that the gas chimneys are going beyond the seal, that this will lead me to, and it will let me conclude that I have a very high risk, which can be caused maybe by the leakage of the hydrocarbons. Lastly, and as a conclusion, I would say that since the 1960s to present, number of fluid indicators became available for interpreters. So I would say that we are very lucky, because we came at a time where we have many choices and options, not like maybe 20 or 30 years ago, where you have maybe only intercept times gradient, or maybe you have near minus offset. Also, I have to say that there is no attribute which can work for all conditions. There is no magic. There is no attribute which can work for all geologies, but you might find some factors or fluid factors which can work for X geology and may not work for other maybe geology. And also I have to say that the performance of the fluid indicators depend on the local geology and also the data quality and also the petrophysics and rock physics. So different geological conditions, different petrophysical conditions and rock physical conditions might lead to different results using maybe the same fluid indicators. And we have seen this, for example, in the case of Poseidon 1 and Poseidon 2 and Kronos 1. Also, it's highly recommended that all the fluid factors are all assessed and evaluated one by one, and you choose which one will provide you the best maybe results. So, and you can even include and extend your interpretation as fluid interpreter to find maybe some expressions in the frequency. But you have to remember that all the time that good interpretation will start all the time from good modeling. So if you can model your attribute, then go ahead and try to interpret it. But if you can model it, here the risk of uncertainty and the ambiguity might be quite high. Lastly, the development of fluid indicators and testing them actually will require collaboration between industry and research institutions and also universities. As a university, for example, we cannot do all the work. If the companies and if the maybe the industry will not provide us with problems and with data set, and maybe oil industry, maybe they don't have the time which we have, for example, in universities. So they cannot do too much work. They cannot do too much scientific work, development, literature research, and maybe development and maybe coding, programming, learning, as we do. So, and I would say that we will complete, and this is the way we work, and this is the entire world, and this is the world, the universities, how they work, and the oil industry, how they work. For example, Leon Thompson, who is very famous in anisotropy, is from the University of Houston, Castania, University of Houston, the Professor Marfort from the University of Oklahoma, the Xia from China University of Geoscience, and many more examples. They are all belong to universities, but they are working with oil industries, and they are continuously publishing their work, their results, which are a result of collaboration between all the teams and between all the parts, between all the geoscience community. Lastly, I would like to thank Inas for this invitation, for this talk, which I hope it will bring certain maybe benefit and certain information to you. And also, I would like to thank the DGB Earth Science for providing Open Detect software and Geo software for providing also the Hamson Russell software. And also, I would like to thank Geoscience Australia for providing the data set used in this study. And thank you very much.
Thank you very much, Professor Farfour, for the very, very interesting and exciting lecture. I really enjoyed it from the start to the end. So you really covered all the basics, starting from the basic theory, and then you covered basically 40 years of AVO analysis, introducing machine learning role, as well as some final case study showcasing how we can implement seismic attributes and AVO analysis in oil and gas exploration. So I would like to remind our audience that you can ask your questions to Professor Farfour. I already see many questions on the chat box here. I will pick a few of them. So let's go to the Q&A session. Let me first pick a question from our audience. Okay, so first question is from Facebook. Is there any attribute that characterize fracture to employ it in DFN, the district fracture network? So maybe he's asking about structural attributes, some advice on structural attributes and how they can be implemented for fracture modeling.
Actually, this is a good question, and especially in AVO, there is another branch of AVO which is especially for fractals, which will control the variation of the amplitude with azimuth. So we can control the variation of the amplitude over the azimuth. So we can assess the amplitude at different angles, and this might be, or any change of this kind of amplitude with azimuth, it might be attributed or it might be associated to maybe anisotropy, which can be caused by this kind of fractals.
Thank you.
This is what
Thank you very much, and so I pick up another question as well from the chat. Thank you very much for the presentation. Can you please highlight the novelty of the AVO approach you developed compared to the previous ones?
Okay, thank you for this question. What I would say here, I would say that attributes which myself and Douglas Foster and myself and John Castagna, we have proposed an attribute or fluid indicator attribute because we have found that most of the attributes they are using the RP and RS, the reflectivity of the P wave and the reflectivity of the S wave, where we can sometimes they are not available all the time, and even in some software you cannot find the RP and the RS. So what we have tried to do, we have tried to propose and we tried to see the fluid expressions from intercept and gradient point of view, and we tried to come up with another expression of the fluid factors with the help of intercept and gradient, not the RP and the RS. So it's a kind of another version of the fluid factors, which were developed firstly by Smith and Gidlow and then improved by Fatty and others. And so what we are doing actually, we are giving another expression for the fluid factor, but in terms of intercept and gradient. We have tested them and we have published them in the SEG annual meeting, and you can find them in the SEG library.
Thank you very much, Professor. We'll pick up another question from LinkedIn this time. Thank you, Professor, for this fruitful presentation. My question is regarding the changes in elastic property. Could that be related to poroelastic stress change due to the oil and gas depletion mentioned?
Definitely, and this is a very good question. Unfortunately, most of the time when we talk about fluid and elastic parameters interpretation and seismic amplitude interpretation, most of the time we ignore the fact of maybe overpressure or under pressure. But at certain time or nowadays, we should not forget and we should not ignore it. Why? Because we have many problems and we have many issues, and now we do have the facility to do that. And now we have the new branch of geophysics or geoscience, which is the geomechanic. In the geomechanic, we can also do some kind of, or we can extract some kind of fluid of attributes which might indicate for us whether the change in those elastic properties are due to pressure or overpressure or under pressure or fluid. So now I believe the geomechanics is very nice field, very evolving field. So and maybe if I will try to give another talk like this one, I will include geomechanic definitely. Thank you for the point.
Thank you, Doctor. So we're really looking forward to have you anytime within us again. Thank you very much. So we will pick another questions. Actually, we have comments and questions from YouTube here. Abdelkader Jiddou. Bonjour, Monsieur Amrouche. D'abord, je vous remercie pour l'effort que vous êtes en train de fournir pour organiser ces intéressants workshops. So, merci, je vous remercie, Monsieur. And also, another comment. Bonjour, Monsieur Farfour. Ça me fait un vraiment plaisir de votre nom associé avec les grands noms des chercheurs de ce domaine comme Foster et Castagna. So it's also our big pleasure, and we're very proud of Professor Farfour to do such a breakthrough in this research. And he's also asking a question in French. Est-ce que vous avez testé ces fluid factors in the carbonate reservoir? So he's asking if he already tested these fluid factor in carbonates. And this is also taking me to another question. Maybe you can add some comments on what kind of attributes are recommended between carbonate formation and silicoclastic reservoirs.
Very good point. Actually, in Oman here and in most of the Middle East, most of our reservoirs, they are carbonate, and most of the work must be done on carbonate. So actually, we have already finished the testing these kind of attributes on clastic reservoirs. And now we are in the stage of testing the carbonate, testing these fluids on carbonate reservoirs. I can just summarize what we have found so far. We have found that most of the fluid factors will work, especially if we have a very clear drop in VPVS of the reservoir compared to the host rock or compared to the surrounding rocks. If you don't have a clear drop in VPVS compared to the host rock or compared to the overlying rocks, we cannot expect maybe a fluid expression. And this can happen also for carbonate reservoirs and also for tight sandstone. For the carbonate, we have tested most of the fluid factors and we have found it was just synthetic model, and what we have found in the normal case, because most of the carbonate, they have very large VPVS. So even if you have a fluid which will cause the drop of the VPVS will remain higher than the host rock. So we have tested it more and more, and we have tried to decline and to reduce the VPVS until we reach a value or a quantity of the VPVS below the VPVS of the host rock. Then the fluid expression starts to be expressed. So this is the conclusion which I can give you here in this webinar. So the key point in all AVO attributes is the VPVS. If you found that the VPVS, and actually Ostrander in the 1984 already mentioned this, and he started actually talking about the AVO from Poisson ratio point of view. And now we came to the point that if you have drop in VPVS, which is below the VPVS of the host rock, then you can see your fluid responses in any type of reservoirs. But if you cannot, even in clastic, you cannot see your fluid expressions.
Thank you. Thank you very much for the conclusion, Professor, and for the feedback. So before closing, I myself have another question, so maybe we can end with it. You know, since the beginning, you showed many formulas when it comes to AVO modeling. You know, you have ACHI and Rickards approximations, Zweipritz approximations, Chouet second term, Chouet third term. So which one to use based on our lithology? And from your experience, what would be the one that you recommend, let's say, for reservoirs in Hassim Saud or in Algeria in general?
Okay, thank you very much. Actually, as you mentioned, we have many different approximations, and all are trying to simplify the Zweipritz equations. So now, which approximation I should use? For example, I have shown that we can use, for example, the Aki-Richard, we can use, for example, the Gray and others, the Russell and others, and also Castagna and others. So the approximation which I will use, it depends on my final objective, which kind of attribute I want. For example, if I want the RP and the RS, I will use the Fetty and others. If I'm interested in maybe the Poisson reflectivity or maybe the intercept, I will go for the Aki and Richard. If I will need to go for the lambda rho or the delta lambda, or the reflectivity of the lambda and the reflectivity of the mu, then I have to go to Gray and others. If I want to go to the reflectivity, the fluid reflectivity and the mu reflectivity, I have to go to Russell approximation. So it depends on which project or product you want to get from the AV.
Thank you very much. So it's not based on the lithology of the reservoir, but rather based on the output we are looking for. Thank you very much, Professor. I think with that said, I would like to close this very interesting talk today. I would like to thank you very much for accepting to present to be part of our keynote of our webinar series, and I would like also to thank all our audience. We remind you that we are still holding monthly webinars in US International Network of Algerian Scientists, where we invite specialists in the oil gas to discuss specific topic. For next month, we are going to have Dr. Steve Cuddy, who is going to discuss how we can improve reservoir modeling using fractals. So we will talk about reservoir 3D modeling. Again, thank you very much, Professor Farfour, for your comments, and we'd like to thank all our audience for today. And have a good day.
Thank you very much. Thank you.